Hi, everybody. It's Professor Mitchell. This is the moment we've kind of all been waiting for, Section 5.1, Verifying Trigonometric Identities. So all of those sections that we just reviewed in Chapter P were to prepare us for this section because we're going to be using a lot of algebra tricks in this section. So in this section, there is one and only one objective: use the fundamental trigonometric identities to verify identities. So the first thing we need to do is review what are the fundamental trigonometric identities. They are all the ones that we learned about in Chapter 4. So first you have your reciprocal identities. So every trig function is the reciprocal of another trig function. The sine and the cosecant are reciprocals of each other. Cosine and secant are reciprocals of each other, and the same thing for tangent and cotangent. And those are called your reciprocal identities. These are going to come in handy in this section a lot. One of the tricks that you're going to learn for verifying identities is when you have a bunch of trig functions that are not sines and cosines. One trick that often works is to turn all of those functions into, or write them in terms of sine and cosine. So for example, if you have a cosecant or a secant, it's often helpful to write that as 1 over sine x or 1 over cosine x. If you have a tangent or a cotangent, what's often helpful is to write those in terms of sines and cosines, and you do that using the quotient identities, which say that the tangent of x is the sine of x over the cosine of x. The cotangent of x is the cosine of x over the sine of x. Next, we have our Pythagorean identities. So hopefully you remember that this one right here is super, super important. This one you should know in your sleep. These other two, I think I've mentioned to you before, these are the ones that I don't trust myself to remember. So for example, every time, I'm aware that there is an identity that relates tangent to secant, or I should say tangent squared to secant squared. And I'm aware that there's an identity that relates cotangent squared to cosecant squared. But I don't trust myself, even after all the years I've been doing this, to remember, okay, is that identity 1 plus tangent squared x equals secant squared x? Or is it 1 plus secant squared x equals tangent squared x? Instead of possibly getting it wrong, what I do is I just take this identity, which I do know in my sleep, and if I know I need the one that relates tangent and secant, I divide every term of this identity by cosine squared x, because I remember that the tangent is the sine over the cosine. So I know that that's going to give me a tangent squared. This is going to give me a 1. And then this thing over here is going to give me the secant squared. So when I divide everything through by cosine squared x, what I end up with is tangent squared x plus 1 equals secant squared x, which is exactly what this says. And then if I need this identity over here, I do the exact same thing, only I divide everybody by sine squared x. So if you can picture that, I'm not going to write it out here. Sine squared x divided by sine squared x would be 1. Cosine squared x divided by sine squared x, that's using this identity, would be cotangent squared x. And then 1 over sine squared x would be cosecant squared x. All right, next you have your even odd identities. I want to say we went over these in about section 4.2, maybe. So remember, the only two trigonometric functions that are even are the cosine and the secant. Those two are both even. The other 4 are all odd, which is kind of special because most functions in general are neither even nor odd. All right, so the trigonometric functions are all one or the other. Cosine and secant are even. The other four are all odd. Okay, so we might be using those once in a while. Then you have your, okay. That's all you have. Those are all the identities that we're going to be using in this section. All right, so now we're ready to start verifying identities. First of all, what is an identity? An identity is an equation that is always true as long as everything in the equation is defined. Okay. So, you know, simple example, x plus x equals 2x is an identity. All right, it's always true no matter what you plug in for x. So to verify an identity, we show that one side of the identity can be simplified so that it is identical to the other side. Okay. Each side of the equation is manipulated independently of the other side. So, and this is a little pet peeve of mine. A lot of times students who are new to doing this, which is almost everybody, will try to work with both sides at the same time. Don't do that unless you get absolutely desperate. All right, most of the time you can start with one side, and it's usually going to be the side that's more complicated, that looks more complicated, that you want to start with. All right, and start playing with that and simplifying it and see if you can turn it into the other side, right? You can, so for example, if I start with the right side, because the right side looks more complicated, I'm going to start trying to simplify it and using my fundamental identities, and I'm allowed to peek at what the left side looks like that I'm trying to turn it into. I just don't want to keep writing it over and over. All right, that's kind of a rookie mistake. And they do say that right here, right? Start with the side containing the more complicated expression. There are some exceptions to that, but 9 times out of 10, that's what you're going to do. If you substitute one or more of the fundamental identities on the more complicated side, you will often be able to rewrite it in a form identical to that of the other side. And let me say one other thing about this, which is that you're not always going to do the right thing on the first try. I don't always even do the right thing on the first try. All right, sometimes you have to experiment. You try one thing, okay, that doesn't seem to be working, I'll try something else. Okay. All right. Here we go. Okay. So we want to verify the identity cosecant x times tangent x equals secant x. Okay. So the more complicated side is definitely the left side, right? So I am going to start with the left side. And they're kind of giving away the strategy right in the title here, right? Changing to sines and cosines. So that is often a good strategy when you have tangents, cotangents, secants, cosecants involved, is try just turning everything into sine and cosine using the reciprocal identities and the quotient identities and see what happens. So in this case, I am going to rewrite cosecant x as 1 over sine x, right? And then I'm going to write tangent x as sine x over cosine x. So this is my reciprocal identity. This is my quotient identity. And you see what happens, right? When you multiply these two fractions together. Okay, so this is just what I said out loud. So the PowerPoint, I noticed that in a lot of these, they'll write the reason next to the step, which is kind of nice. Okay, but of course the signs cancel, right? Because you have one upstairs, one downstairs. So that leaves me with 1 over cosine x, and of course 1 over cosine x is just another name for secant x. That's it. Done. That is a pretty easy one. All right, example 2. For this identity, we're going to use factoring to verify it. So again, start with the more complicated side, which is again the left side. So I'm going to take sine x minus sine x cosine squared x. And I am going to factor out sine x, all right? So one of the things that's tricky about this section, I think, is that we just practiced all this stuff with plain old variables, all right? So picture this saying x minus xy squared, all right? And that would be, you know, that would be a pretty easy factoring problem. Well, now the x has been replaced with a sine x. So you have to learn to see that you can factor out the whole sine x. So if I talk about my thought bubble again, you know, you notice that sine x is a common factor. And by the way, you can't factor out a sine without something like an x attached to it. Remember, sin by itself doesn't make any sense. It's not a variable, right? It's a function. Okay, so it's kind of like I'm dividing out sine x, but not really. And so after I make this point, I'm going to erase that because that's actually not technically correct to write that. I'm just showing you what the other factor would be. So the other factor would be 1, right? Here's the 1, and then cosine squared x, right? So one factor is sine x, the other factor is 1 minus cosine squared x. Okay, so now I am going to use my Pythagorean, oh, and that was just factoring. Now I'm going to use my Pythagorean identity to rewrite 1 minus cosine squared x as sine squared x. And let's talk about that for a second. So earlier I showed you one of the Pythagorean identities. Let me just see, what do I have written over here? Oh, perfect, perfect, perfect. So the one that I showed you was sine squared x plus cosine squared x equals 1. So we're just writing that in a different form where the sine squared x is by itself. That I really think of that as being the same exact identity, just being in a different form. Okay. So 1 minus cosine squared x got replaced with sine squared x. Whoops. I messed up. Erased too much. Anyway, you know what I'm trying to say, right? I subtracted cosine squared x from both sides. Okay, there we go. All right, so now we're just about there. We have sine x times sine squared x. So I'm going to multiply those together, and it's technically using the product rule for exponents. 1 copy of sine x times 2 copies of sine x gives you 3 copies of sine x. So that's, again, just using the product rule for exponents. It's just like doing an x times an x squared. Gives you x cubed. All right, and that identity is verified. Okay, example 3, combining fractional expressions to verify an identity. This was exactly the reason that in section P6, I wanted to review adding and subtracting rational expressions. Okay. So we want to verify this identity, sine x over 1 plus cosine x, plus 1 plus cosine x over sine x. Supposedly that is equal to 2 cosecant x. Wow, how does that happen? Well, we'll start with the side that's more complicated. Can we all agree that that's this side? Okay. And what I'm going to do is I'm going to add these two sides together. So you notice, of course, they don't have the same denominator, which means I have to get a common denominator. So how am I going to do that? Okay, there's a lot to unpack here. The least common denominator would just be sine x times 1 plus cosine x. So these are different factors. So the LCD would have to include both of them. So the way that I am going to make this expression have denominator sine x times 1 plus cosine x is I am going to multiply the top and the bottom by sine x, right? And the way that I'm going to make this expression have that denominator is I am going to multiply the top and the bottom by 1 plus cosine x. Okay. So now those two expressions have the same denominator. Okay. Now, what's happening in this step is we are multiplying sine x times sine x to get sine squared x. Remember that sine squared x, when they put the exponent there, is special shorthand notation, which means the sine of x squared, all right? Nobody ever writes it like this. It's traditional to write it the way that you see there, but that's what that means. Okay. And then 1 plus cosine x times 1 plus cosine x, that is basically FOIL. So when they FOIL this, 1 times 1 is 1. And then 1 times cosine x is cosine x. Cosine x times 1 is another cosine x. So they have already combined cosine x plus cosine x into 2 cosine x. And then finally they did cosine x times cosine x is cosine squared x. All right. So we have these two expressions that now have the same denominator. So what's going to happen between here and the beginning of the next slide is that we're just going to add these two together, all right? So as big and scary as these look, all these are just two fractions with the same denominator. So when I add them together, the sum is going to have this denominator, and it's going to have all this stuff in the numerator. And that is what you see right here, okay? So here is the numerator from new expression number 1. Here is the numerator from new expression number 2. Okay. So I believe what's going to happen next is, and this is one of these things that comes to you with practice. You see this sine squared x, and you see this cosine squared x. Okay. Can you guess what I'm going to do with those? I'm going to add those together, and actually what they did was they just moved them so they're next to each other in preparation for what I'm really going to do, which is that I'm going to turn those two things added together into a 1, right? Because sine squared x plus cosine squared x is 1. Okay. Using that Pythagorean identity. All right. Good. And then 1 plus 1 is 2. All right. I like steps like that. Okay. All right. So now notice that in this numerator, 2 plus 2 cosine x, you have a common factor 2. So what I'm going to do now is factor out that common factor 2. And so picture what that's going to leave me with. It's going to leave me with 2 times 1 plus cosine x. And that's what you see here. And then they started doing a second thing in the next step, which is that there is a common factor now between the top and the bottom. So when you get rid of that common factor, you're left with 2 over sine x. And what's another way to write 2 over sine x? 2 times cosecant x. Boom. All right, that brings us to example 4. Now they call this working with both sides separately to verify an identity. I don't think that's really necessary with this one, but we'll do it that way. If you're watching this at home, I'm going to ask you to pause the video and try this, because this side here, I think you're going to do something kind of similar to what we did in the last example. So pause the video, try it, and then we'll compare notes. All right, let's compare notes. So I would start with the left side. Notice these are they're fractions that have different denominators, and so I'm going to make them have the same denominator. And the way I'm going to do that is my common denominator is 1 plus sine theta times 1 minus sine theta. Okay. So the way that I'm going to make these two things have that denominator is I'm going to multiply the top and the bottom of this one by 1 minus sine theta. So that's what you see here. Multiplying the top and the bottom by 1 minus sine theta. And then multiply the top and the bottom of this one by 1 plus sine theta. And they put these in sort of a weird spot. Okay. All right, so now they have the same denominator. So I'm going to keep that denominator and I'm going to add the numerators. So notice that these two things are just being multiplied by 1. So you can ignore the 1 and just put a 1 minus sine theta plus 1 plus sine theta. Okay. And you might be able to see where this is going. The next thing that's going to happen is the minus sine theta and the plus sine theta are going to cancel out. Okay, so this and this go away, right? And then 1 plus 1 is 2. Okay, so now we have 2 over 1 plus sine theta times 1 minus sine theta. Let me see if they're going to do anything else with that. I know what I would do. Ah, good. Okay, so this is in the form difference of two squares, right? This is just like a 1 plus x times a 1 minus x. And as you know, a 1 plus x times a 1 minus x is a 1 minus x squared. So that becomes 1 minus sine squared theta. And let's see what's next. Okay, so now they have decided to leave that alone and start working with the right side. So let's see what they did with the right side. They took 2 plus 2 tangent squared theta, and they used a quotient identity to turn tangent squared theta into sine squared theta over cosine squared theta. Okay. All right, and then let's see. It looks like they got a common denominator. All right, so let's work this out. Go back to, okay, so if you think of this as 2 over 1, and you think of that as 2 sine squared theta over cosine squared theta, they're trying to get everybody to have the same denominator. So they multiplied the top and the bottom of this 2 over 1 by cosine squared theta. And that's how they got 2 cosine squared theta over cosine squared theta. Okay. All right, so now we have 2 cosine squared theta over cosine squared theta. We're adding that to 2 sine squared theta over cosine squared theta. They have the same denominator. So that's going to turn into that. You just add your numerators. All right, so what we're going to do next is factor the 2 out of this 2 cosine squared theta plus 2 sine squared theta. And that gives you this. So hopefully some alarm bells are going off. Cosine squared theta plus sine squared theta. That is equal to 1, right? So this thing here turns into 2 times 1, which is just 2. And then they use the Pythagorean identity to write cosine squared theta as 1 minus sine squared theta, which hopefully you remember is the thing that they had turned the left side into. Okay. So, Working with the left side, they found that that came out to 2 over 1 minus sine squared theta. Working with the right side, they found that that came out to the same thing. And because both sides simplified down to the same thing, that verifies the identity.